Now that we know a lot about enols and enolates, we're ready to do reactions with them. And the first electrophile that we're going to look at is halogens. There are three reactions under halogenation that's in your book in section 22.2. And so we're going to go over them sequentially. And the first one that we're going to look at is reacting enols or enolates, so it's under both acidic or basic condition, reacting with halogen, which could be Cl2, Br2, or I2. So this is the mechanism by which it would occur. So this is like an overall mechanism. So the first one is under acidic conditions, and the second one is under basic conditions. So just want to kind of briefly go over those general mechanism first before we look at specific individual reactions, right? So since we looked at how enols form, so the mechanism really starts with the enol here. And the electrophile is some kind of halogen. And so as the arrow shows, the enol will reform the double bond, and then C double bond C grabs a halogen. So you could sort of think of this as a alkene chemistry that you had in 114, where you were doing addition reactions of double bonds. But in this case, you're only going to react at the nucleophilic carbon atom. So then this grabs an X to form this bond here. That's the new bond that you form on the alpha carbon. It releases X minus, which then grabs the extra proton because this is plus charged. And then the final product is alpha halogenated carbonyl compound. All right. So the overall reaction in reacting with halogen is that you have a carbonyl group, and you have some kind of halogen, and a lot of times it's done under with the presence of pyridine, because HX is liberated, and so pyridine acts like a base in soaking up the HX. So then you basically have C-1 still, because you are putting the electrophile, which in this case is halogen, on the alpha carbon. So that's the overall product that you would get. All right. So if you were to do problems like this, where it's an unsymmetrical ketone and you are reacting, for example, with Br2 and pyridine, then what would happen is you would have an alpha halogenation reaction in which you would have brominated either here or here. You have choice now. And because you're forming an enol and it's an equilibrium process, you're going to form the more stable thermodynamic enol, which would be this. And then that will go on and halogenate. So basically you would always form the alpha halogenation product on the more substituted carbon in these cases, because of the equilibrium happening, in which even if the kinetic enol formed, it would go back to the starting material and form the more stable, thermodynamically more stable enol. All right. Now under acidic conditions, there's another reaction called alpha bromination of carboxylic acid. It has a very long fancy name for it, which you don't have to know, but basically you have a carboxylic acid and you have an alpha proton, and the reagent is PBr3, and this reagent, what it does first is to do an acyl substitution, in which you form an acid halide first, And then that equilibrates to an acid halide enol. See the double bond here. And this intermediate then reacts with Br2, just like you've seen before, and forms a halogen at the alpha carbon, just like you've seen before. And this acid halide that has been substituted at the alpha carbon is not a very stable compound, so when you do a hydrolysis at the end, this acid bromide basically goes back to the carboxylic acid. So the overall reaction is you have a carboxylic acid and you are reacting with PBr3 and then hydrolysis. Essentially you are still getting the carboxylic acid and you're putting the bromine alpha to it, to the carboxylic acid. So this carbonyl of the carboxylic acid is serving as the function of other carbonyl that you've seen to form the enol in order for the alpha halogenation reaction to occur. All right, so that's what's happening under acidic conditions. So under acidic conditions is basically alpha halogenation reaction of either ketones, aldehydes, and then carboxylic acid, as you've seen here. Under basic conditions, the mechanism would follow in which you would have enolate ion available in equilibrium with enols and the keto form. So this is the enolate anion, and because it's under basic conditions, this is what would be reactive. And so even though in enolates you have a negative charge on oxygen as well as carbon, and theoretically the oxygen could go and react with an electrophile, but that's not commonly seen. But the oxygen, the negative charge is used to reform the C-double-O, and then the carbon, alpha carbon, is what goes after the electrophile. So essentially this is this carbon is what is attacking the halogen, and then forming this carbon halogen bond on the alpha carbon and reforming the C-double-O. All right. So an example of the basic halogenation reaction is on haloform reaction, as you see down at the bottom on the third, as a third reaction. So the overall reaction for haloform is that whatever carbonyl you have, you're going to halogenate it to the alpha proton. So let's say you have cyclohexanone and you have the haloform reaction occurring, then what you have is, so you have under basic conditions, and then let's say you have a bromination occurring, then what is happening is you're forming enolate, in which it's going to brominate. So let's say you brominate, right? And this is not the finished product, because this hydrogen, because now it's got next to a C-double-O, which is the electron withdrawing group, because this carbon is electropositive, but then you have halogen, also electronegative atom, pulling electron density towards it. So this proton, after the bromine adds, is even more acidic than the other protons. So it keeps halogenating on and on and on until all the alpha hydrogens has been replaced with bromine on both sides. So it's hard to stop when you're doing under basic conditions after one halogenation, because this proton is more acidic. And remember, because we're doing under basic conditions, this is going to get deprotonated as soon as it forms an enolate, and then goes and reacts with another Br2, on and on and on. So this is the final product that happens. All right. So one of the interesting thing that this reaction is used for, the haloform reaction, is methyl ketones in the lab. So you have an unknown, and you see whether or not you have a methyl ketones. So this test for methyl ketone is called haloform reaction, and this is the reaction that you're essentially doing, where if you have a methyl group at the end, then under these conditions you are going to form, so this is going to be an R group, CBr 3 times, right? And let's say on the left side there's no alpha proton. So let's say this is what's happening, all right? This actually is not isolatable because it's not stable. Because what it does is, because this is now a good leaving group with 3 halogens, it gets attacked by the base that's present. That's what's shown here. And once the base adds and then the O- comes down, then this leaves as a leaving group. And the reason why this is a good leaving group is because it's got 3 electronegative atoms attached to the carbon, making this negative charge stable. So what it forms is carboxylic acid, and this is, it's got the negative charge, so it goes after the acidic proton, and it forms this bromoform. If you did it with iodine, it would be iodoform. And that usually precipitates out of solution. And by looking at the precipitate, especially with iodine, you form an iodoform. And that, by observing that there is a precipitate forming from this methyl ketone, that's a positive sign that you started with the methyl ketone. So that's the byproduct, and that's what you're looking for in this test for methyl ketone in this reaction. All right, so under basic conditions, you halogenate every alpha proton there is until it's all substituted for halogen. Under acidic conditions, you are just halogenating once on the alpha carbon, both with carboxylic acids and ketones, as shown here. All right. So that concludes this lecture, and you should be able to do this drill question, in which I ask you to react with the bromine after forming the enol or enolate, depending on, so you should be able to do both under acidic and basic conditions as well. And at the end, you should be able to do 22.9, 22.11, and 22.13 as well.